Hello friends, today we are going to start with the second chapter from Unit 3, Planning in AI. Now, in the first part today we are going to see the components of planning. But even before that, let us understand what is planning. So we have seen different problem solving strategies that can be used to solve AI problems. We have also seen different knowledge representation mechanisms. These two can be combined to solve AI problems. It is often useful to divide the problem that must be solved into smaller pieces, okay, and to solve these problems pieces separately to the extent that is possible, okay. Now, when this occurs, this mainly occurs when we are addressing a complex problem, okay, and usually in AI, especially in the areas of robotics and so on, the problems are not, they are complex, they are not simple, right? So when the task at the hand is complex, it is always better to try to divide it into smaller pieces and then to solve those pieces separately. So this is a place where planning comes into picture. Planning helps in construction of plans for solving problems pertaining to complicated domains. Now, what is a plan, right? So I'll just give you an example. If you want to prepare an omelette, okay, initially, what are the things which are required to prepare an omelette? You would probably require an egg, you would require some other ingredients, and so on. So these are your things which are required for you to start preparation. And then you will have some set of procedural instructions. Execute instruction 1, and only after that is finished execute instruction 2, then 3 and 4, and the outcome of this would be a soft, fluffy, delicious omelette. Similarly, plan is nothing but the set of steps, okay, that are to be executed, or set of actions that are supposed to be taken for us to solve a problem and get to a solution. So that's a plan. Planning usually comprises of decision making tasks performed by the robots or computer programs to achieve a specific goal. The execution of plan is about choosing a sequence of actions with a high likelihood to complete the specific task. So as I was just telling you, we are dealing with sequence of actions. Okay, and to get that sequence, there are different methods that we're going to see here. One of them is goal stack planning. So plan is nothing but it is when you have set of actions that can be taken, plan is nothing but sequencing or sequence of those actions, okay. So if the actions are executed in that particular sequence, you're going to get your answer solution, okay. So that's a plan. Now, in this planning, we are going to take an example of a block world problem. Okay, a block world problem. I have already discussed this in the first unit, but let us revisit this block world problem. Usually, this block world problem is, a nursery level problem that's given for the kids. Okay, so there are these blocks, okay, cubes, cubical blocks, which are of the same size. Maybe each block will be having a different color, or maybe some different alphabet will be printed on that block. And when these blocks are given to the students, to the kids, teacher asks the kids to come up with a particular placement of the block. Okay, so this is a kindergarten activity, but let us take that example, okay, in a slightly complex domain, wherein now to pick up those blocks and to place them back, to arrange them in an order, we are going to also make use of a robotic arm, okay. So this is the robotic arm that is going to do all these activities, okay. So to be specific, the block world environment, it has square blocks of the same size. Blocks can be stacked one upon other. There's a flat surface you can consider table on which the blocks can be placed. There is a robotic arm that can manipulate the blocks. It can hold only one block at a time. Now let us see what are the possible actions that this robotic arm can perform. Okay, the first action is called as unstack action. Okay, now you must have realized that I am using a predicate. So the predicate is read as A unstack B. Now this unstack action is basically what? It picks up a block A from its current position, that is on top of B. So look at the figure. Now what is happening here is there are two blocks, block A and block B. Block A is residing on top of block B and the robotic arm is empty. So unstack action is the one wherein robotic arm will pick up this block A which is currently on top of block B. So that is called as unstacking action. So looking at this particular figure, we can easily figure out what are the preconditions which are required for this action to execute. I have already discussed about this, but I will again tell you. See, whenever you take a particular action, there are always some preconditions which are supposed to be true, which should be satisfied. Only then you can take a particular action. Now, once the action is taken, then some more set of conditions will be true, or these are called as post conditions or effects of the action after taking it. Okay, now in this particular example, what are the preconditions? Looking at the figure, the very first simple precondition is that for this unstack action to occur, the robotic arm must be empty, and second, block A must not have any other block on top of it, so that robotic arm can directly pick up block A. If there is another block which is present on block A, then can robotic arm pick up block A? No, it will have to pick up the topmost block first. So the preconditions for unstack action here are the robotic arm should be empty and block A must not have any other block on top of it. Now, once this action is taken, what will be the effect of the action or the post conditions? Okay, the effect will be that the arm which was free, now it will be holding that block A, whereas block B will be clear. That means there won't be any other block on top of block B. That's called as block B being clear. So unstack is the first action. Second action is stack. Now stack is exactly opposite action. Placing block A on top of block B is called as unstack. It's called as a stack action. Consider the figure. Now for this stack action to occur, your robotic arm must be holding a block. So when I say stacking, when I say block A is stacked on top of B, robotic arm must be already holding that block A, and block B should be clear. There should not be any other block present on top of block B. Only then stacking can happen. Okay, so the precondition is that the arm must be already holding block A and the surface of block B must be clear. Only then stack action can be executed. So these are the preconditions. Now once the stack action is executed, what are the effects of post conditions? Post condition will be that once A is already placed on B, okay, now A resides on B, okay, and robotic arm is now empty. So these are the post conditions of the stack action. Third action robotic arm that can take is pick up A. Now pick up means picking up a block A from the table and holding it. So as you can see in this figure, pickup action is the one wherein robotic arm, which is empty right now, will be picking up block A and holding it. Now there is a slight difference between unstack and pickup action. Both actions actually removes a block and the hand holds it. But in case of pickup action, pickup and put down actions can be executed for a block who is directly residing on the table. Whereas stack or unstack action, okay, is the one in which, for example, stack is the action wherein you are placing a block on top of another block. Unstack is the action wherein you are removing a block which is residing already on another block. Whereas pickup is an action when you are removing a block who is present directly on the ground or the table. And next you will also see a put down action, that is putting down the block which the hand is holding directly on the table, not on top of any other block. So that is put down action. Now the preconditions for this pickup action is that one, the robotic arm must be empty, and the second thing is there must not be any other block on top of A. Only then pickup can be executed. The effects of post conditions of this action will be that the robotic arm would be holding block A. The last action is put down A. Put down means block A is put down on the table. So the precondition for this put down action is that in order to put down A, arm must be already holding block A. Only then it can put it down. So the precondition is that arm must be holding block A. Effects or post conditions for this action will be that once the block is put down, the arm becomes empty and the block is now on table. Okay, now just realize that every time that I specify precondition and post condition, how are we going to represent this pre and post conditions in the machine? Okay, we have already seen 4 actions and we have represented these actions in predicate logic. Okay, unstack, stack, pickup, put down. But to also consider or to also represent these preconditions and post conditions, there has to be some more predicates, right? Also, you notice that the robotic arm can only hold one block at a time. This is an assumption that we are doing. Okay, now so we will require some supporting predicates to represent preconditions and post conditions. Okay, so in order to specify both the conditions under which the operation may be performed and the result of performing it, we need the following predicates. On A comma B. So first predicate that I'm going to use is on A comma B. You read it like this: A is on B. That means block A is residing on block B. So this is on predicate. Second predicate that we are going to use is on table A. Okay, kindly note there is a slight mistake here. It is not on tables, it is on table. S should not be there. Okay, so on table A, it means block A is on table, it is directly residing on the table. Third action, clear A. That means there is nothing on top of block A. That means block A is clear. Fourth, holding A. That means the robotic arm is currently holding block A. Okay, you need to remember these predicates. Let's move on to the next thing. Okay, one last predicate, arm empty predicate. Now arm empty predicate is the one wherein if it is true, that means robotic arm is holding something. Okay, if it is false, I'm sorry, arm empty predicate, if it is false, it means the robotic arm is not holding anything. I'm sorry, arm empty predicate, if it is true, it means the robotic arm is not holding anything. And if it is false, okay, that means robotic arm is holding something. Yes. Components of planning. So what are the different components of planning? The first component is choose the best rule for applying the next based on the best available heuristics. Now basically when you're going to do the planning, as we have already discussed this, you remember in the first unit there was a method called as mean and analysis. Okay, and we had taken up a problem wherein a person wanted to move from one particular place in Delhi to a particular hotel in Mumbai. Okay, and then we had seen the sequence of actions. We had seen what possible actions can be taken. So walking was an action, uh, taking bus, taking cab was an action, taking flight was an action. Okay, and so on. So these were so many actions, and then at the end of this mean and analysis, through the forward and backward movements, forward and backward, uh, problem solving, we had seen how we get the sequence of these operators, how we get the sequence of the operations, and that sequence that we got is actually the plan that we came up with, right? So remember, how did we start with that problem? The very first thing that I said was, since the person has to move from his house in Delhi to a hotel in Mumbai. Okay, out of all the possible actions that are available, like walking, taking bus, taking cab, taking flight or fly action, which is the best action that you're going to take, or which is the action that you're going to consider first? Remember that time we said we will consider fly action first. Why? Because that is the only action that was reducing the difference or the distance between both the cities to maximum extent. Okay, the precondition for that taking flight or fly action was that if the distance between the source and the destination is greater than 3200 kilometers. Okay, so that time we said we started with fly action because it was the best, if we consider that particular action, and it is going to maximize, it is going to minimize the difference between the initial state and the goal state. Okay, it is going to minimize the distance in kilometers between the initial state and the goal state. So compared to all other actions, we said we will first take fly action. But then further we said, for fly action to be true, some preconditions of fly action should be satisfied. So we went into uh, uh, backward way. Okay, and then we went into forward way. So basically it was kind of finding a mean, and at the end we came up with an order, particular order, right? So what we did there was actually kind of planning, right? So the first component of planning here says the same thing. Choose the best rule for applying the next based on the available heuristics. In that problem, the heuristic was the distance in kilometers. Okay, and based on that, we chose the best rule, that is fly over there. So this is the first component of planning. The second component of planning is apply the chosen rule for computing the new problem state. Okay, now once out of all the possible rules, once you have chosen the best rule, second step says apply the chosen rule for computing the new problem state. Now in this domain, okay, in planning, this step is pretty difficult because earlier, in earlier modules, we weren't dividing the problem into sub problems. Okay, but now in this particular chapter, what we have started is, we are trying to break up a bigger complex problem into smaller sub problems, and then we are trying to solve these sub problems individually. As a result, the set of actions that we consider, okay, won't be so much simpler. Okay, because some actions might be required for sub plan A, sub problem A. Some actions will be there only for sub problem B, and so on. Okay, so ordering can be affected in this case. Fine. So we will see how we can go about doing this second step, second component. Let us proceed. The third component of planning is detect when a solution has been found. Okay, so when how are you going to detect that the solution is found? Okay, you will have your initial state, you will know what goal state is required. So at every new state that you generate at every stage, you have to compare that current state with the goal state, and the time when the current state is going to be very close to the goal state or almost the goal state. Okay, that time you can say the solution has been found. Okay, you may not get the ideal solution in most of the AI problems, but then the most nearest or the most feasible solution, okay, will be considered. So this is how this is the third component of planning. Fourth component of planning: detect dead ends so that they can be abandoned and the system's effort is directed in more fruitful directions. It can so happen, as you go on choosing the actions, you can visualize that it's a tree. Okay, so every action that you take it takes you from the parent node to the child node, and whenever you are at a particular node, you will be having multiple options or multiple actions that you can take. You are going to select the best option, now best with respect to the current scenario, but later on it can so happen that somewhere down the line, if you feel that yes, you have reached a leaf node which is also not the solution node, so that's called as a dead end. In that case, your planning here would be hampered. So what you have to do in such cases is you have to abandon the search in that particular branch, because anyways you have reached the leaf node, or maybe the heuristic value has you know crossed the threshold or whatever it is, and you have to backtrack and select a different branch which could be more fruitful. So this is the fourth component of planning. And fifth component: detect when an almost correct solution has been found. Okay, so the difference between the solution and almost correct solution is that, okay, when I talk about the solution, it may not be the ideal one, but yes, it's a solution. Now, almost correct solution is the one which will not give you the answer, but you miss by some points, or you miss at a very close distance. So these are something called as almost correct solutions. Now you should since it is a play of experience. AI is basically a play of experience. Detecting almost correct solutions as you again and again solve problems becomes very important, crucial, because agent is going to get experience from this, and based on this the new heuristic values will be populated. Based on this, later on in the next next time, you are going to find out, you are going to understand, your agent is going to understand that yes, this particular path may not give you the answer, so better switch the path. Accordingly, heuristic values can be changed and so on. Components of planning, let's go into detail. The first component that we saw is choose the best rule for applying next based on the best available heuristics. Now, the method here is to find a difference between the current state and the goal state. So, once you have set of rules which can be applied at this moment, for every rule you find out what will happen if I apply that rule. So, find out what is the difference between the current state and the goal state if the rule is applied, and then choose that rule among n number of rules which reduces the distance most effectively, like what we did in that mean end analysis by considering the fly action. Example: an agent wished to travel by car to visit a friend. Okay, so what are the different steps it is going to take? Okay, the very first thing is, since you're traveling by car, first you're going to go to the filling station and fill the car with petrol. But suppose if you don't own a car, then you will have to first go to the showroom, buy the car, and then do this particular step of going to the filling station, right? So the largest difference must be tackled first. Yes. The second component of the planning: apply this rule to create a new state. Okay. Now, in the previous problems that we have discussed before planning chapter was discussed previously, when complete systems were specified, applicability of a rule wasn't very difficult, right? Because everything was observable, kind of, right? But now, since you have split the big problem into sub problems, okay, the task is now difficult. When AI problem is decomposed into sub-problems or parts, we must be able to handle rules which only cover parts of the systems. So there was one approach by a person called as Green. We call it as Green's approach. So this Green's approach, it states that we have to note only the changes to the state produced by application of a rule. Okay, this Green's approach says that whatever changes will happen to the state after a particular rule is applied, so you have to note the changes to the state. As an example, okay, of how to create a new state. Okay, I'll take the block world problem again. Consider the problem of having two blocks A and B stacked. So let's say A has to be stacked on top of B. Let's say this is the problem. Okay, block A has to be stacked on top of B. Now, so using Green's approach, okay, the initial state S naught can be described. How it can be described? Now, you and me, we can see the world, we can perceive the world. But for machine, although there are cameras, although there are perceptors, okay, how are you going to represent the current state of the world, right? So Green said that the current state can be represented with respect to frame axioms, and these frame axioms are nothing but these are the predicates, right? So the current state that you can see can be represented so that the computer understand what the state is using predicate logic, okay, is as follows. Now, what can you see in this particular current state? The first thing is block A is on block B. So I'm going to use that on predicate. So the first predicate is A on B, right? And I'm assuming that this is initial state S naught. So Green said one way of representing the current state is by writing the different predicates which are true in that particular state. Okay, so first thing, to describe this state, first thing, A is on top of B, right? So block A is on B in state S0. So this is true. And what else? Block B is directly residing on table. So B is on table in state S0. And okay, A is clear. That means there is no block on top of A. So A is clear in S0, right? He said that any state can be represented with respect to this kind of frame axioms. And we have already discussed what is a clause. When different predicates are connected with or, that is a clause, right? Here, this is one clause, this is one clause, this is one clause. So this is basically what? It's a clausal form. So for this state to occur, 1, 2, 3, all these three predicates together, if they are true, this is true and this is true and this is true, when all three are together true, then it describes this state. But notice that there is also a robotic arm which he has ignored here. Okay, we will talk about it after some time. Okay, he has taken only these three predicates because the problem was having block A on top of B. So here the arm was not into picture, so that's why arm is not there. But yes, this can create a serious issue which I will discuss after some time. Let's go ahead now. So we have already written a frame axiom that describes the current state. Now let's say if we wish to unstack A from top of B, if we wish to unstack A from top of B, then Green said that each operation like stack, unstack and so on can be also represented using his approach. Example, unstack x comma y. Now x and y are general variables. At any point of time, x can be A, x can be B and so on. So unstack operation can be represented using Green's approach like this. Okay, let me tell you what this means. So since this is a rule, okay, every rule has left hand side and right hand side. You already know. Left hand side is nothing but these are preconditions that should hold true before an action is taken, right? And the right hand side is basically the effect of taking that action. Okay, now the action that we're going to take is unstack. Now when can you take this unstack action? Can you take unstack action here? Yes, because the preconditions are satisfied. So see, on left hand side in these brackets, he has represented the preconditions for unstack action. First thing is, block X should be clear. See, if you want to unstack X which is currently present on top of Y, so here X is nothing but A and Y is equal to B. Okay, here X is equal to A and Y is equal to B in our problem, correct? So precondition for unstacking is block A, that is X, should be clear in state S, and block A should be on top of block B in state S. A means X, B means Y, and only when these two things are true, then you can apply this unstack action. Now, after taking this unstack action, the post conditions are represented here on the right hand side. Now, what is the post condition? Once A is unstacked, what will happen? Robotic arm will be holding A, right? So the post condition of this is holding X comma, that means X means A, so it means the robotic arm is holding X. Now, how he is holding X? By doing the unstack operation of X comma Y in state S, and after doing this we go to resultant state T. So from state S we go to state T. That's the meaning of it. Looks complicated, but this is one way how rules or actions can be represented using Green's approach. Now, so next, suppose unstack operation is performed using this, then what will be the change in state? Okay, so the change in state will be this. Okay, earlier, before action is taken, this was the current state. Okay, uh, clear predicate was there, on predicate was there, and say on table predicate is there. Okay, and then after this action is taken, okay, in the new state the robotic arm is holding block A in state S1. So from S0 we go to S1 state, correct? But again the people will have some doubts, okay, and that doubt is this: I have specified, or with this we have specified that robotic arm is holding A, but after A is holded by the robotic arm, why are you not specifying that block B is now clear? It's not specified. Also note that the transition have happened from state S0 to S1. Block A was on top of B. Now after the transition in state S1, block A is in the robotic arm, correct? But what about block B? Block B, which was earlier also on table, now also it is residing on the table. So that means block B, its position is not changed. But do we have to specify this to the system, or system will assume this, right? So as you can rightly see here, the Green's approach has the most common disadvantage, and that is, although Green said that a current state can be represented with the frame axiom, how many frame axioms are you going to write? How many predicates are you going to write? Now this is a very simple domain. Okay, it's a very simple domain, but in realistic situations, whenever you perceive a particular thing, there might be so many things happening in the environment, right? So what all are you going to consider? It is very difficult to consider all the preconditions for me to decide what action to take place, because I may ignore certain preconditions, I may assume certain preconditions, right? So this is one issue. Second issue is, in Green's approach, after taking an action, there might be some conditions which are not changed. There might be certain things which are not changed. So uh, you will have to explicitly specify what is not changing, right? Similarly, suppose there is a robot agent who is teaching, automated teacher, okay, and there is a student in the class for a particular lecture, Now that the teacher has told the student to go out and get some book, okay, the robotic teacher, after this, can the robotic teacher understand that once the student goes out, he is still not present in the class, or you will have to explicitly tell him this? So with the Green's approach, we will have to explicitly tell the system that student has gone out. It means student is not present in the class, because the system is not intelligent actually. You have to make it intelligent by doing this, correct? So let us now see what are the problems with this Green's approach. The first problem is called as frame problem. It is difficult to specify all the conditions that remain unaffected after the application of an action, right? It is difficult to specify all the conditions that remain unaffected after the application of an action. So according to that same example which we discussed, this was my state S naught, and using Green's approach, the state was represented like this: on a comma b S naught, and on table b comma S naught, and clear a comma S naught, and so on. This is before the unstack operation. After this unstack operation, the state changed to S1, okay, and it was represented using holding a in state S1. Okay, now please note, state B, which is on the table, even after the action, state B still block B, which is on the table before the action, okay, unstack action, after action is executed, also block B remains on the table. But does it get reflected here? Is there a on table predicate specified here? No, right? So you will have to explicitly write this in the action called as unstack, which he has not written. Now here it's not a mistake. It is because for a simple problem you can specify all that what is happening and all that which is not changing, all that which will change, and so on. But for a more realistic domain where there are so many things to observe, it is not really possible to specify which are the things which have not changed in the particular picture or in the particular perception, right? So this is a frame problem. It is very difficult to specify all the conditions that remain unaffected by application of action. So block B's position has remained unaffected, okay, but it has not been specified here with Green's approach, right? Second problem with Green's approach is a qualification problem. So what is qualification? See, for an action to execute, it should be qualified for that action, right? That means there should be some precondition, those are to be satisfied. Now qualification problem refers to this: it is difficult to specify all the preconditions that must be satisfied for an action to be eligible for the application. Like I said, what are the things that don't change? It's difficult to specify. Similarly, what are the preconditions? What are all the possible preconditions for a particular action to be applied is also difficult to be specified. Maybe for a simple domain like block world, which I have shown you, it is possible. You can figure out each and every minute thing. But for a more realistic domain, okay, it is very difficult, because in the world there are so many things which are happening when you perceive the environment. There are so many things which will be happening in the environment. How many things are you going to observe, right? So coming back to this Green's approach example, before unstack action, this was the thing, and this is what we saw after unstack action. So here qualification refers to, do we need to specify that arm is empty? Okay, see here, these were the preconditions for unstack action to take place, but we only specified here what A is on top of P, and then we also specified that B is on table. Why we specified this? Because for unstack action, which was specified using Green's approach, these were the only two preconditions, left hand side values, that were given. Okay, but and also clear is there, but we have ignored arm, robotic arm, correct? So do we need to specify that arm is also empty as part of precondition, right? So this is an issue. This is called as qualification problem. So everything, all preconditions cannot be specified. It is difficult. Ramification problem. It is difficult to specify all the effects or post conditions that will become true after the action is carried out. Right? Again here, taking the same example. Do we need to specify that block B is now clear? Right? Here see, after the unstack action has been occurred, okay, according to the Green's approach, okay, the right hand side of that unstack action was having only holding predicate. Okay, now you see that after after the robotic arm holds the block B, okay, it is still on the ground, but it is clear also. There is nothing on top of that block B. Okay, so will the machine understand this, or you will have to specify this? You will have to specify this explicitly. So how many things are we going to specify one after the other? It is difficult. So do we need to specify that block B is now clear after taking action? Yes, you will have to. Okay, so this problem is ramification. Okay, because you cannot specify everything or all the effects that will become true after action is carrying out in the realistic domain, in the real environment.